Hello everybody, welcome back to another physics video with me. Today is going to be a little bit of a deviation from the problem solving series. The actual howitzer is in this room today, so we'll see how filming goes. What are you doing? Let's see if we can get him on camera. Come here. Hi. Oh, you're being so bad. Don't knock my coffee over. Okay, anyway, back to the video. So today is going to be probably the most, I should have this disclaimer on every video, but this is going to be the most tailored to the lab section of the class that I am a co-instructor for. I don't know if this is going to be the same standard across other universities or even other like AP or high school physics classes. This is actually the first place that I've encountered this is going to be using uncertainties and your error propagation. I'm going to be switching over to the iPad and then talking over just because it's a lot of weird notation and like using Greek letters and things like that it's not as easy to just type out and pop up on a screen, and I think it's just easier to see these in action since error propagation doesn't work the same way that other equations work, and it always causes a ton of problems. I will say all the information I'm going to be going over is in the beginning sections of the lab manual for P201 and I believe P202, any of the other intro courses. So always refer to that if you're not at, again, this specific university and this specific class, because that is where my expertise is and that's where the information for this video is coming from. So without further ado, we'll jump into the iPad screen record and get into talking about error propagation. So before we get into actually showing error propagation in the examples, I just want to really quickly go over where the uncertainties come from when we're talking about lab course. So within lab, you're typically going to be measuring physical quantities multiple times, and then you would represent the value of that quantity by the average plus or minus the standard deviation. Then these measured values get put into equations, and the uncertainty that you get from the standard deviation is then going to propagate into whatever those measurements are used to calculate. So the standard deviation from these measured values is going to be the same thing as our uncertainty. I'm going to shorten that as uncert just because uncertainty is a long word and I'm going to have to write it a lot. So if we have some value A, we would represent that as the average of the measurements plus or minus the standard deviation of those measurements, but because standard deviation is the same as uncertainty in this case, we're going to write it with the uncertainty notation, which is a lowercase Greek letter delta with that letter A, so little delta A. Now, we have two different types of uncertainties. We have absolute, which is just going to be some number that has the same units as the average or of that physical quantity that we're looking at. So for acceleration, it would be meters per second squared, something plus or minus something meters per second squared. We also have relative, which is writing the uncertainty in forms of a percentage, which is good when you're comparing the uncertainty across different physical quantities, so like acceleration and velocity. And we get relative from taking the absolute uncertainty divided by whatever the measured value is, or the average, and then multiplying that by 100% in order to get it as a percentage. Now that we've talked a little bit about what's going on with the measured values, let's see how they work when we put them into calculations. So let's say that we're going to be solving for some calculated value, capital A, which is a function of all of these measured values, little a1, little a2, little a3, so on and so forth. And this function can be addition, it could be any combination of the mathematical operators that we're used to thinking about. Now, in order to get the value of A, we would go ahead and just plug in all those average measured values that we have for all of those little a's. So we would just go ahead and put in A1, A2, A3, and all the averages for that, and that would give us the value of A. However, if we want to get the uncertainty in A, we don't want to go ahead and just take that function and plug in all of the uncertainties. So I'm going to switch over to red so that you absolutely know that the uncertainty in A is not going to be substituting in the uncertainties for those measured values. Instead, what we want to do is we're going to I'm going to write this not using those deltas just because it could be relative or it could be absolute. So if you're writing the uncertainty in A squared, that's going to be the uncertainty in A1 squared plus the uncertainty in A2 squared, and so on and so forth. And these uncertainties either all need to be absolute or they all need to be relative. And that's going to depend on which operation that we're doing. So for addition and subtraction, that's going to be using the absolute uncertainties. Part of this reason you can actually see when we do the example is because the units are going to be the same. So that's going to make a difference in using absolute, whereas for multiplication and division, you have to use relative because you can multiply and divide different units by one another, in which case we need a equal comparison across quantities, which relative will do. There is kind of a trick that you're supposed to be able to use to memorize this, that add starts with A, so does absolute, and that division is also a ratio which starts with R, the same as relative, but in lab you usually get your notes, so if you just want to screenshot that, you can go ahead and keep it on you so that way you can remember it and you don't have to memorize. So let's get into some examples. So let's say that we have C equals A plus B, and A, I'll just say, is equal to 5 plus or minus 0.5. B is equal to 7 plus or minus 0.1. And I guess I'll make these masses, so I'll put some units on there of kilograms. In order to get C, we're just going to take, so that's going to be, again, remember, a number plus an uncertainty. And in order to get the number, we're just going to add the 5 and the 7 together for the measured quantities of A and B, which will be equal to 12. But for the uncertainty, we have to use that squared equation. So we have to use the error propagation equation with the absolute uncertainties. So our uncertainty in C will be 0.5 squared plus 0.1 squared, all under a square root, which is equal to 0.5. And I think this goes against the sig fig rules, but I'll put in a 0.51 in there just so that you could see that it's different from either of the other uncertainties, and that'll have the same units of kilograms. So we can write C being equal to 12 plus or minus 0.51 kilograms. Now let's switch over and look at a multiplication division example. So I'll just pre-introduce you guys to the fact that you're going to be dealing with weird variables that all look the same later on. So since we use lowercase d for distances most of the time, for density we use this rho. So I'm just going to use that density is mass divided by volume, and rho is just another Greek letter. We'll say the mass is 1 plus or minus 1.1 kilogram, and that the volume is going to be 100 plus or minus 1 meters cubed, I think. Yeah, we'll use meters cubed. And I write the V a little fancy just so it doesn't get confused with velocity, which can sometimes happen. So again, rho is going to be a number plus or minus an uncertainty. The number will just be our 1 divided by 100, which will be 0.01 kilograms per meter cubed. And for the uncertainties, we're going to use the error propagation. So there isn't technically another unit for relative uncertainty versus absolute uncertainty. So typically what I will do is I will go ahead and just write instead of this. So the way that I have it written here is perfectly valid if you know that those have to be relative and they have to be percentages. But in case for some reason that's not the case, you could also just cross that out. And this is the way that I prefer to write it, just so that you could see, keep those variables specifically for absolute and then just write relative in terms of those. So I'll do the absolute divided by the value times 100% squared is going to be equal to again, the uncertainty over the value times 100%. Now I'm adding the squareds. Forgot those. And then, so we did that for rho, for m, and then we'll do the same thing for v. And then we can go ahead and plug in the absolute uncertainties and the values for m and v. And ultimately, since what we're solving for is entirely what we have written out on the left-hand side, we can just leave that as it is. So 0.1 over 1 times 100% squared plus 1 over 100 times 100% quantity squared, all under a square root to just get rid of that squared on the uncertainty, the relative uncertainty and the density. And that'll come out to about 10% squared plus 1% squared, which is about 10%. So then we can go ahead and write our rho as 0.01 kilograms per meter cubed plus or minus 10%. Now let's go ahead and look at if we have combinations or if we have more than one. We don't just have all multiplication or all division, but we have some combination of addition, subtraction, multiplication, and division. So first, let's say that we have D equals A minus B over C. Our first step is going to be to first get the absolute uncertainty from the numerator. So because those two guys are being subtracted from one another, we would use the error propagation formula using absolute uncertainties to just first get that whole numerator represented as a new number with a new uncertainty. Now, because the next step, because the next step is going to be a division of that numerator by the denominator, we're going to have to convert that absolute uncertainty you get from step 1 into a relative uncertainty before you can do step 2. So there's almost like a step 1a and a step 1b. But then step 2 is we will do the error propagation for the whole fraction using the relative uncertainties. Now, on the other hand, if we have D equals A over B plus C, now we need to do that division first. So we're going to do error propagation for that fraction with our relative uncertainties first. Again, there's going to be this kind of step 1a and step 1b, where after you go ahead and get the total relative uncertainty for that fraction, you're going to have to put it into an absolute uncertainty, so that way you can do step 2, which is then the error propagation of doing the addition operator. So then you would be doing error propagation with absolute uncertainty. So you just need to make sure you remember to do that conversion before you sub in and use those. So now using variables, I'll just go through kind of the steps. For A minus B on that right side, to get the uncertainty in A minus B, it'll be the uncertainty in A squared plus the uncertainty in B squared, all under the square root. Then we're going to have to convert that absolute uncertainty into a relative uncertainty. So that'll be the uncertainty in D will be the uncertainty in A minus B over A minus B times 100%. I totally wrote this in the wrong spot. whoops, not guys. Those should all be squared, plus squared of uncertainty in C over C times 100% squared. Then I'm not going to make the same mistake on this side, so I'm going to erase those steps. And for the first step, we're going to get the uncertainty of A over B, which is going to be equal to, first we have to write it in terms of a relative uncertainty. So we'll divide by that A over B, and that 100% should be in there, times 100% quantity squared equals the uncertainty of A over A times 100% squared plus the uncertainty in B over B times 100% squared. Then once you have that, we will have a final number that comes out from this that you'll be able to set equal to that relative uncertainty. So we'll have relative uncertainty written in my longhand way is equal to some number. And then once you have that number, you could go ahead and rearrange that to get the absolute uncertainty. So then you can use the second step of error propagation, that the uncertainty in D is going to be equal to the absolute uncertainty of A over B squared plus the uncertainty in C squared. And again, just to really isolate, we're going to get that number from converting the relative uncertainty to the absolute uncertainty. And then based on, which I don't think that they usually care whether you give absolute or relative, but just make sure that you're always keeping that percent sign on or the units on so that whoever is grading your lab report can distinguish. And just so long as you have one of them, that should be perfectly reasonable for your lab report. In case anyone wants to know Howitzer's actual size for reference, get over here. He's so mad. He wants to go play in the snow so badly. Say happy physicsing. Say bye to the kiddos. I know you're so mad at me. Bye.